So hey guys, I'm back again after seemingly a long break. Uh, so I had to sort out few of my college work, and yeah, I'm back again. So yeah, I also had a haircut, and as you can see. So this easy maintenance, so smaller hair, easy maintenance. So so back to what we were doing. We were doing in Lexus, right? So Lexus and generation of tokens. So I handled about keywords, identifiers, then decimal, hexadecimal, binary, octal. So all of this were handled. So now we have to go through our syntax and semantic, right? So that's our agenda today. Syntax and semantic. So, so let me start like our Upendraji's style of reverse screenplay. So let's start from from theory of computation perspective, like how we write grammars. So how do we write grammars? So we have a starting point called program, okay, which is a non-terminal. So terminals are the endpoints, right? So program is where we are going to start. Okay, that's the root place where everything begins. Then we have a statement, which is not a terminal. Okay, statements. Then statements further would expand to block statements, else statements, variable declaration, variable assignment, while statement, do while statement. So what are these? Block statement, block statement. Remember, we have this one you see, right? So whatever is within this curly bracket, this your block statement. And variable declaration. What's variable declaration? Variable declaration is like, see, we have int x, this your int x. So x has been declared. So or you directly do int x equal to 10, right? That's also a variable declaration. So that's your variable declaration. Then you have variable assignment. What's variable assignment? Say you did x equal to say 20. Okay, that's your assignment. Then you have else statement. So I did else statement here uh, because I'm reinforcing that from else statement, before an else statement, we have an if statement in C, right? So that's what I'm replicating here. So I'm enforcing if statement should come before else if statement. And we can have any number of else if statements, right? That's why I put the star there. So it could be zero or more than zero else if. And after that, we have the else block. And the else block will start with else and then followed by this one, right? We'll have the keyword else, then followed by the block statement, right? This one. And within this, we could have another set of statements. So that's what I'm replicating, yeah. And this if statement would start with if keyword, and then within these brackets, we'll have conditions. And here we would have the condition. And this condition, if it is true, it goes into this block. we then execute whatever is there within the block statement. Right? That's a if statement. So again, after this if and this expression, and expressions again not uh, terminal. It's also going to expand further to primary expression and the expression. So primary expression as in it's integer literal or an identifier, or it could be an expression again. So as in like this condition could be, so it started from Fred. So this the expression. So in expression we have primary expression. So it could be like if then. So in C programming, within this bracket, if we have a non-zero value, it's going to evaluate to true. So this one is going to evaluate to true. So then we'll go into the block statement, right? So this is our int literal part of our primary expression. Okay. Or otherwise, we would go into uh, primary expression directly. See, it is primary expression operator. Operator would be these operators into division, modulus, and all these operators. Okay. And further, again, it could be expression because we could have this way also, right? 10 into 10, which is 100. So we could have expressions as this as well. So that's why I handle that over here. Okay. And, and this one. So it could be a primary expression, just 10, or it could be an expression, an operator, and an expression, as in this form. This form. So to handle that, I did this primary expression. So primary expression is an integer literal or an identifier or an expression with this one. So it could be like this as well, right? X. So this X is our identifier. So identifier also should be there. That's why I included identifier. So instead of this 10, I could also have here as X. So identifier. To handle these kind of situations, I put this one expression with primary expression, operator, and expression. The expression again would come back here with primary expression, operator expression, or just primary expression. Okay, so that's what is expression. So after that, we'll have again the block statement. Block statement again could be any of these, right? Any of these statements. So block statement, within a block statement, we can have another block statement, right? So if we have this block statement, within this we can have again another block statement, right? And within this we can have another if as well, right? If. So that's what I'm doing now. So block statement is nothing but set of statements which is capsuled with this curly bracket. Okay. So that's what it is. So similarly, we have variable declaration, which will start with int. It has to start with int, right? Always declarations always start with the variable type. Then we do this. In my case, I have only handled integers, so it is int x. If I would have handled character, it would be char x, right? So then identifier. So identifier is it's a terminal. It's not a non-terminal. So when we reach identifier, we are going to stop. We are not going to go further. So after identifier, we would have a declaration chain. So now you need to understand declaration chain. So declaration chain is like this. Like you would have it is int x comma y comma z, right? So that's what the chain is. So after this x, we would have this comma, right? We would have this comma and any number of identifiers we would have, right? So that's why I put this, and then after that we'll have the semicolon, or we would have this identifier equal to some expression like say y is equal to 10 into 10 into say 10 into something uh, a, and a is already predefined before. Okay, so to handle that, so this expressions again will be handled over here, right? Okay, and also we'll have this way, as in we'll have directly x equal to, okay, x declaration chain. Okay, after this we'll have directly say might be x equal to uh, then identifier chain. Okay, x equal to 10 maybe y, the y and any number of identifiers z, w, okay, any number, or we might have this one. We might have also like y equal to 10 into a kind of thing, yeah, and semicolon. Okay, so those things are handled in this declaration chain. So right after identifier, we could have comma. So that's handled over here. Or right after this identifier, we would be having directly this expression. Okay, so that part is handled over here. As in this part is x equal to, it could be x equal to this. So if it is x equal to this expression, it comes to this part. If it is not this, it is just x comma, then it would come over here. And if it is also with the expression, then it would come this way here. Okay, to handle this kind of situations. Okay, so that is what declaration chain and variable declaration will handle. And then we have variable assignment. We have variable assignment as in like we will have already int x equal to 10, right? And say I'm doing x equal to 20. Okay, so that part. So variable assignment. Variable assignment is first we need an identifier. So identifier x. Okay. After that we have assignment operators. Assignment operators could be equal, plus equal. Like instead of this, we could have this as well. So what will this do? Yes, this will change x equal to 10 plus 12 plus 30, right? So x will get changed to 30. Okay. So for that reason. So all of that will be handled. All of these assignment operators will be handled. So assignment operator followed by the expression. Again expression. Why expression? Because I would be having like uh, 20 into some a, and say a is something like int a equal to 2. Okay, so here will be 20 into 2, which is 40. 40 plus 10, so x is going to be 50. Okay, so to handle that, I put after assignment expression. Then finally we'll have the semicolon, right? Finally here we'll have semicolon, right? So that, and as for while statement, it has to start with while keyword. Then we'll have this condition, right? What's while? This while, this is our while, right? Within this, just like our if condition, we'll have an expression here, right? Which has to be valid true. Only then we'll go into this block. So that is what has been done earlier. So within this, we'll have expression, and then we'll have a block statement, and then followed by do while. We'll have do, then block statement, then while followed by the condition, the expression, and then we have the semicolon, right? So in block statement, yeah, here we require the semicolon. In do while we require the semicolon. In while loop we don't require it, the semicolon. While loop we have it just like this, right? But in do while we'll have do, and then over here we have while. After the block statement we'll have while and while this way, right? Have the expression. So that's been handled earlier. Okay. So that is the gist of it, of entire thing. So I wanted to start here so that you'll get how this been implemented in code, because the exact thing I have done in the code. And yeah, one more thing apart from the DOC grammar, there's also semantic, right? So semantic is mainly based on our symbol table. So the symbol table, I have to give an example for that. Okay. So we have int a equal to 40 here, right? And for this scope, excluding the block statement here, for this scope, like this one, actually in fact including the block scope, this a will be visible here in the block scope, and entire this global, right? This a is global to all variables, so its visibility is global. But this a within this block statement, it's not global, right? So it is within the block statement, and within the block we have another block, right? This block. So and within that block we have this int b. So this b's visibility is only up to this block. So outside it's not visible. So now we have to maintain symbol tables for this global. Globally, we need to maintain a symbol table, and within this block statement, we have to maintain a symbol table, and within this block statement, we have to maintain a symbol table. And main thing, very important thing is that see above this we have this block, right? So what are variables there? We have to be able to access it in this block. And above this, we have this global, this one, these a equal to 40, which is visible, right? That also should be visible in this block. So that also should be taken care of. So we need a symbol table, and we need a collection of pointers of this each symbol tables. So, as in, like globally, we'll have a single table. Okay. Globally, we'll have a single table. Okay. So, say it is G global single table is being created. Say, okay. Using say malloc I created, and I have a pointer to that table. Then what I do is I maintain a simple table for this block. So say this is block A. Say this one is block A, and within it we have block B. So block B is within block A, right? So now for in block A, we need a single table. So we create a single table for that. And then similarly, when we reach here, block B. So for block A, we have created a single table. And now at block B, we need to create a single table. So when we create a single table for block B, okay. So we created a single table for block B. So when we create it, we have a pointer for it. Now we are creating another uh, pointer to pointers. Okay, pointer to pointers. Why? Because we need to access this table at this scope. At this scope, see here int b is equal to x, right? Say if I had another variable, uh, here a x y z is there, right? So if we say another variable b equal to 40, b equal to 30, right? Okay. So if I write here b equal to b, this b should reference to this b, right? Because here we don't have a b. Within block A, we don't have a variable b. In globally, we have b equal to 30. So that should be referenced here, right? So how do we get that? For that purpose, we'll have a pointer, okay, say stack, stack kind of pointer, okay, stack kind of data structure, stack tables, okay, stack tables. Now within that stack table, first this global would be pushed, okay. Then next block A would be pushed. Then block B would be pushed. So the topmost element in the stack is block B's single table. And when block B is, so when we do this, we have to go through the stack and read, can we do this B equal to B? So we have to be able to read from top of the stack to until the bottom of the stack. Say we have a size, okay. Each time, say size equal to 0. Uh, say this tag table, we put this one, stack tables, we made size equal to 0. Now when we push this global single table, okay, then we increment the size. Okay. So now size is 1. So we'll access, how do we access an arrays? Say this is an array or a pointer to a malloc. Okay. So how do you access? We access from 0 to size minus 1, right? 0 to size minus 1. Size is 1, so 0 to 0, so first element. Now again we push this tag. So size is now 2. Okay. Size is now 2. Then finally here size is now 3. So 0 is this, 1 is this, and 2 is this. Okay. So when we are doing this, we have to be able to read all variables associated with block B, also block A, and also global single table. So we need a for loop which would go from size minus 1 to 0. That's what I'm saying. Okay. So we need to have this. And whenever we are out, when we get out of this block B, it should be destroyed. And when we are destroying, we are also destroying the tables associated with it. So block B table will be destroyed and size becomes 2. And then when we get out of block A is also destroyed. So its symbol table also gets destroyed. And then finally, when we get out of the program, we also destroy this global symbol table. And finally, size will become 0. Okay. So that's the idea here. So that's the idea here. This how the semantic is working over here. So that's the gist of syntax and semantic. So let's go through the code to understand it. So last time we looked at Lexer, and Lexer would give us the collection of tokens, and that tokens is to be passed to our parser, and Lexer would increment the number of tokens. Okay, so that number of tokens is passed into parse function, and that parse is handling my syntax and semantic. This is my main.c main function. This is the entry point of entire code. Yeah. So, so, as I told in previous, few videos, I did mention that dot h is where I'll mention which file, which functionality should be visible to the outside files. Okay, like to the main function, which all should be visible, or say here in parser, I am also calling other, right, token related. So there is a token related token. So if you look at this token, so I made this token here. I mentioned this token in the header file, right? So that's why it's visible over here in parser.c. So okay. So back to this one, parse. And this is the functionality. So this is exactly what I was saying. So I am creating a scope stack. So the scope stack. Okay, let me show the scope stack. So this scope stack is a pointer of pointers to table. So it will contain all these tables that I was talking about, So these. So this is a pointer, right? This global symbol table is a pointer, block A symbol table is a pointer, block B symbol table is a pointer, and these pointers are pointing to its corresponding symbol tables. So now this scope stack is a pointer to this pointer. So it's a double pointer. So that's why it's a double pointer. So we'll have a size and a capacity. So capacity is the capacity of that malloc. I'll be creating a malloc for this, right? So as the size increases, I would have to reallocate the heap, right? The space in the heap. So I use realloc based on size. Okay, I'll show that. Uh, Let me just show. Um, so as based on size, if size is greater than the capacity, I'm making a realloc. Okay, so I'm doubling the size, doubling the capacity. Right now, whatever capacity I have, I'm doubling it and I'm reallocating. So that's what I'm doing. So when file parse. Okay. So this is the scope stack I was talking about. Then this is the global symbol table which I was talking about. This global symbol table. So I'm creating at first itself the global symbol table and I'm pushing it. I'm creating. I have a create symbol symbol table and I have a create scope stack. Okay. So this create scope stack is creating a stack. So I'm creating a size of scope stack. Okay. And then the tables. Initially, I am keeping, 8 tables. So here we have three, right? So initially I'm allocating space for 8 tables so that, I don't have to repeatedly call realloc. So that's wastage of time, right? So I'm first itself I'm allocating 8 tables. Okay. So like as in I'm keeping a capacity to store 8 tables. So that's why here malloc 8. Okay. And then I'm setting the size to 0 because I have no size and means I have I'm just initiating the stack, right? So I haven't pushed any table yet, so that's why size is 0 and capacity is 8 because right now my capacity is I can hold up to 8 tables. Okay, so that's why capacity is 8. So back to parse. So that's what create stack is doing. Similarly, this create symbol table. So this function, what is symbol table? Symbol table will have our symbols, right? As in our variables, symbols or variables, the identifiers, right? So symbol table will that is also having a size. Okay, it should also have a size because how will symbol table be? Say this global symbol table. Okay. Uh, Let me take example. Let me take the same example. Yeah. So here in my global symbol table, what all would I have? So my global symbol table, I'll have A, right? I'll have A first, right? Then corresponding to A, I have 40. And then what else I have? X. X is assigned to 4. So corresponding to X, I have only 4. Okay. And corresponding to Y, I have a value 5, right? 5. And corresponding to A, I have so A already have. So A already have. So I update it to 8. So this is how table works, right? Similarly for block, this was block A, right? Block A. So block A is symbol table. Block A is symbol table. Block A single table. There also I have a variable A, but this is independent. This A is different and this A is different because these are different tables, right? So this A is having value of this global variable A, which is 40. So 40 is assigned earlier. Then X is 3. X is 3 here. Then we have Y. By default, I'm setting value to 0. So Y is 0, Z is also 0. Yeah. So this is my symbol table, right? So I'll have a symbol and corresponding value. So that's why if you look at over here, I have symbols and then I have size of the table and the capacity of the table. Just like the scope stack, I have the size and capacity. To this capacity is used for reallocation. Just like if previously, just like the stack, when size is equal to capacity, I'm doubling the capacity. So if you look at create symbol table, right? Mm, So symbol table. I'm creating malloc. I'm assigning this symbol table. Okay, creating a size for this symbol table. Symbol table is a pointer, right? So I'm only allocating the pointer. Then after that, I have symbols. So this symbols is where I storing the values of each identifier, right? So that's why I have I'm starting with 16 variables. See, symbol table is a this table is a pointer to that entire table. Okay, it's a pointer to this entire table. For example, this global symbol table to this entire table, I'm having a pointer. So this the table, and within that table, I have symbols. Okay, look at symbol. So symbol has a name, type, type as in. So right now only I have integer variables. If I have character, I would have written char no var underscore because var underscore char. Okay, and if I'm not using constant as we get, so if I had constants, I would have written var constant. Okay, so symbols are having name as in the variable name a, x, and y. Then I have the uh, type of the variable, which is integer or character. In my case, I have only integer, so that's the type. And then corresponding value. So a has the value 8, right? So that value should be stored. And then line and column also I'm storing. Corresponding line and column number in the file. Okay, so that I'm storing. That's the symbol. Okay. So that's what I'm doing here. So for this symbol, only I have to have the variables, right? Like 16 symbols I have initiated. So my capacity of symbols, I have assigned 16 symbols initially. Okay. So as in right now, I have three, right? I am assigning it to 16. So beyond 16, I have to use realloc. Okay. So beyond 16, I have to use realloc then. Uh, let's create symbol table. Symbol. In creation, we won't be doing. In creation, we have 16. When we push into the symbol table only, if we add symbol, I have done this. See, if I add into the symbol table, if the just like the push stack which I had here, push uh, push stack I had, right? Just like scope stack, uh, push it to scope. So for this scope stack, whenever the size is greater than or equal to capacity, that's when I'm doing twice the capacity, right? Same, just the same concept. Beyond if 16 variables I have, if I have 17, so I use this add symbol to add into the table the symbols. Right? So I use the same concept here. If size is greater than equal to capacity, I double the capacity and do realloc. So, initially I'll have a space to accommodate up to 16 symbols. So that's what it is. And then, and so push scope, I pushed this scope stack. So what is scope stack here? Into scope stack, I'm pushing this table. Okay. So if you look at push scope, So in push scope, already I mentioned it. So based on capacity, we'll double the size if it is the size is greater than equal to this. So that is about increasing capacity. But in push scope, the main thing is this thing here. Have to push the table into the stack, right? So that's what I was saying about I'll increase the size. And at that size, see, size will be initialized to zero. So at location zero, I'll push the global table. And then next size will be one. So at size one, next table will be pushed. And then in size two. So at size two, next table will be pushed and so on. So the size minus one would give the recent table. So recent table as in like in our example which we saw here, right? This one. So the recent table here is this block B single table. This one, this block B single table. So block B single table will be recent one. So size minus one to zero will be traversing. So size minus one, I'll get block B. Then size minus two, I'll get block A, and size minus zero, I'll get global simultaneous. Okay. So that's how it is. So main part of this push scope is to push the stack and push the table into the stack. Okay. And then we create a node. So the main thing in this see in Lexer the output was token, right? So similarly in syntax and semantic the output is the tree, syntax tree, right? So why is it important? Why is that tree important? So it's important because see, firstly we have to understand. See, Lexer in Lexer token was the output, and those tokens are atomic stuff, right? Like if you have say int x and semicolon, int is a token, x and semicolon. These are the three tokens, right? So tokens are these atomic stuff, and they are further we can't atomic because we can't further divide it, right? Int we can't further divide it. It's a keyword. X is an identifier. We can't further divide it. And semicolon, that's a separator. So we can't further divide it, right? Now what is this is an input to our syntax and semantic phase. So in syntax and semantic, this input, right? So in syntax and semantic, we look at the arrangement and the meaning of those tokens. And the output is that tree. And that tree is an input to our code generation, right? So if you look at over here, for example, I have done uh, left child, right sibling. Left child, right sibling. So right, so I have like the binary tree, we have left pointer and right pointer. So my right side is a sibling and left side pointer is a child. So and what is the importance of this tree? This tree is a input to our code generation, as I told it. So if you look at code generation, so I have a node exit call, and based on that, I'll be creating this one. I told it this move RAX and this RDI values. So based on the node, I'll be creating. So if you look at node exit call, for exit, it's we have to place in 16 the RX register and the argument. So in the node itself, I'll have a value. I'll have a left. Left is my child, right? In that child, I'll have this value, integer value. So that be placed into my RDI. Yeah. So if it's a if statement, I'll have a condition. Okay. And that condition would come from my left. left child. So in if condition, I made a child as the condition. Okay. And that condition, based on that condition, I'll be passing. And based on that, I'll be looking the condition and generating my code. So basically, that tokens would be input to my syntax tree, right? And I'm looking at the placement of the tokens in syntax. So similarly, my tree is input to my code generation. So based on the placement of those nodes, I'll be generating my code. Okay. So that's why tree generation is important in syntax phase. So that's why I have to create a node here. If you look at I'm creating after push scope, I am creating a program node. So program node is the what do you say the entry point to all nodes. So that's why I am setting it. It's a line, and if you look at create node, so you have a line and column. Okay. So that is set to zero. Both are set to zero. So if you look at the node, see node, I made a node structure. That node structure I have left and right pointers, and I have line and column number. So for program, I'm setting the line and column number as zero. So that's what I have done here. I'm setting the line and column number to zero earlier. Okay. Yeah, zero. And if you look at create node, so I'm allocating space through malloc. I'm creating a space. Okay, so node just let's go through node once again. So node has a node type. Okay, node type. If you look at node type, we have a node integer literal binary expression exit call for if statement. I have a node. So basically, for all of this. So all of these non-terminals, I'm creating a node. Okay, I'm creating a node. So binary expression, binary if statement. But for statement, I'm not creating a node. For statement, I'm creating this. No. If statement, I'm creating node. Else if I'm creating node. Yeah. Else if I'm creating node. Else while statement, do while statement, identifier statement, end, and node unknown. Is for unknown type of unknown. And then we have declaration, variable declaration, then type specifier, then assignment. For assignments, we have node for this assignment, this variable assignment. We have okay. Then, then for block also have an yeah. And for begin. So So node begin is our program. Node begin is to say that this the point where the entire tree is going to be generated. This is the root node. So that is node begin. So firstly we create this node. So in node we have this type of node, and then I have a union of integer value or string value. So why is it? Because this see the particular node could be it could be an integer literal, or it could be an identifier. If it's an identifier, I have to store it as a string value, right? Because an identifier. So let's go to this one. So if it's an identifier, I have to store this a, right, as a string. Or say if it was in A, B, C, D. So this A, B, C, D I have to store, right? So that is for that is how I store that through string value I store it. And if it's an integer literal, in that case, I have to store it as an integer value. So I'm combining both. So it could be an integer literal or a identifier. So I'm only using integers, right? So identifier or it could be an integer literal. So that's why I'm combining as a union. So this is a smart way to combine space so that you are reducing the space here. So the same space would be allocated for either integer value, integer it could be a identifier, right? So that is for that, and we have same just like our tokens will have a line and a column, and we have a left side which is child and right side which is the city. And that's about that. And so let's go about this one. So we are creating the node, then we are passing in the type, node type equal to type. So the node type was for program, it was, node begin. So that type will be assigned. Then the line and column number is set to 0. And left and right is currently set to null because we haven't passed the program yet. We haven't passed the tokens yet. That's why. And so if it's an integer literal, so uh, we are assigning it into dot int val. So this value dot int val. So if it's an integer literal, I told you, right? So we'll place it into integer val, or if it's an identifier, I place it into string val. So that uh, value whichever it's passed or either, so that value will be stored into int val. Else, if it's identifier, we are storing it into string val. So we created the first root node, right? We created the first root node earlier over over here. Now is the time you can see this mapping. So this is done. Okay, program node is created. Now I'll have a statement. I have to pass through statements for block statement, else statement, and all this variable declaration, one statement and stuff. Right. So for that, I have this is if root node is null, then I'm just exiting. So I'm creating a current pointer, and then I'm creating a last node. So last node is to point towards the last. Like for example, uh, if I have like this, if I have same say in x, then I have x equal to 10, and then I have in y. Okay. So here last node is going to be this int y, this declaration. First node is going to be int x. Next, we have a sibling. To this int x, we have sibling, this assignment node, x equal to 10. Then sibling to both of this, we have int y. So the last node here is int y. So why I'm keeping this pointer so that it'll be easy for me to assign. See, last pointer would be now int y. Now, next, say I have y equal to 720. So using this last node, I can then do last last nodes right pointer equal to this node assign. So node assign is what? In this case, it is y equal to 20. So that way it'd be easy for me. Yeah. Otherwise, I have to traverse through the tree, right? Traverse through this node and this node and reach the last node, right? So to avoid that, I'm having a last node so that quickly I can take the last node's date pointer and assign it. Because see, what I'm doing here is, see, at statement level, this in all these statements are siblings. But for X, this 10 is a child, right? So as an overview, if you look at this statement wise, these are siblings, right? So for those siblings, sibling, how I'm doing through the right pointer, I'm setting this sibling, and through the left pointer, I'm setting the child. So the last node is here int one. For that int wise right pointer, I'm setting this assignment, this y equal to 20. So int wise right pointer is going to be y equal to 20. See here, I told this right. I'm using this left child right sibling. So here, these are siblings now. These are at same level. That's why they are siblings. So int wise, right? When I right now, when I'm at int y, its right pointer should be set to y equal to 20. If I'm at x equal to 10, its right pointer should be set to int y. Okay. Okay. So this one's right equal to x equal 10. Okay. And this one's right equals and the one and this one's right equals y equal 20. And currently this is the last no. Okay. And next if I have say another say y equals to x plus y. So then I'll do node last nodes right equal to this one. So last node was what? Y equal to this one. So this one's right. This one will be this. And I'm going to update the last node to this one. So last node would be updated to this table. Last node. It's not this table. How will I update it? I do it last node. Now I'll simply do last node equal to last nodes. Right. That way I'm at the next, I'm at the updated last node. So that, so I have this pass statement. Pass statement is exactly going to do this. Let's see if it is a block statement, else variable assignment, while statement or a domain. So you can go to that. So I'll see if it is, if it is starting with an int, then it's a variable declaration, right? It's possibly a variable declaration because we might be having conditions like, if user might have written int and semicolon, in which case we have to give an error, right? But in this case, if it was int x, we have to parse it correctly. So we see the token type is keyword, and if it is int, so it is possibly it's a possible variable declaration. And variable declaration, this part. So in variable declaration, what do we see? See in variable declaration, there was a variable declaration. Yeah, in variable declaration, we'll see if it is int, right? So int we have already seen. Okay, int. If it is not int, we are just returning it. And next we have to expect an identifier. If it's not an identifier, we are exiting. See, after int, we have to get an identifier, right? In this case, identifier is x. So if it's not, identifier, they are just exiting with the exiting one. So any non-zero value with when we give exit, it's error code. Okay. So then, uh, so this identifier, it's stored in ID token. So if it's not an identifier, only we exit, right? So if it is an identifier, we'll store it in ID token. And then, yeah, and then this portion of the code where we have int identifier and declaration chain. So in declaration chain, if you look at, uh, I have this, right, equal to expression, equal to and expression, right? So that's what I'm implementing here. So after identifier, I'm looking at if it is equal symbol. Okay, if it is equal symbol, then after that I expect it to be expression. That's why I have pass expression here. So exactly, see, we are one-to-one mapping of this grammar. So declaration chain is having this parse expression, right? So in parse expression, then parse expression, what do we have? Parse expression. So this expression, in expression, we have primary expression, operator, and expression. So basically, it's recursion. Okay. So this expression is calling itself. So in if you look at in block statement also we had recursion, right? When we're calling block statement, we have statements. And again within statements, if you have a block statement, it's a recursion, right? So exact same thing here in expression. Here in expression. See the block statement, I'll show you again with the example. See, within block statement, again we have a block statement, right? So it's a recursive call, right? You have to call first block statement to get to pass this. Then second, you will have recursion second to pass this. Right? So that one I was talking about. So similarly, expression is expression. Here expression. So expression. Then we have primary expression, operator, and expression. So it's a recursion. So if we look at the parse expression, so we'll parse primary, right? We'll send in the token and to parse primary, and in parse primary, we'll get either an integer literal or we'll get an identifier, right? Either of the two. If it's if it's identifier, we find it in the symbol table. So not the symbol table, the entire scope stack. We had this stack, right? So we have to go through the entire stack and see if we have this variable already defined. So here it's not just syntax, I am also adding semantic, right? So that's why we have to find the symbol. So finding symbol, as I told, we have to go from top to bottom, right? So size minus 1 to 0. That's what I have done. See, size minus 1 to 0 and I minus minus. So I'm finding symbol. Find symbol is find symbol. Find symbol is for the particular table. Okay. So within the particular table, see here, find symbol in scope stack. So within scope stack, we'll have tables, right? We have tables. And within this table only, we have the symbols. So this size minus 1 to 0, we are looping through each of these table pointers. And within these table pointers, within these tables, we have our symbols. So we are looping through each of the table and we are passing in the name of the variable, name of the variable. Yeah. So if you look at here, then we pass in the table and the name. Okay. And now if in that table, we'll go from 0 to table size -1, right? So see within table we have this, right? So in this example we had A, X, and Y, right? For global symbol table. And block A symbol table had A, X, and Y, right? A, X, and Y, right? Also Z also it had. So Z. And in case of block B, this one, this block, it has B, right? B, block B. Block B has B is equal to X, X3. So B is B is 3. Yeah. So now in this code, this one is within that table, we are finding the symbol, right? So here we are going one by one. So at 0, we have, if it's global symbol table, at 0, we have A, which corresponds to 8. X is at 1, so which corresponds to 4. And Y is at 2, which corresponds to 5. 0, 1, 2. Okay. Similarly here 0, 1, 2, 3. So that's what we are doing here. And we are returning the value. Symbols of I. Symbol. So symbol will contain name, is type, into value. So symbol only we are returning, right? So the entire symbol we are returning. The symbol will have the variable name along with its value. So we are returning this as a whole, A and 8. Okay. So we are looking at the parse expression, right? Yeah. Parse expression. Then in expression we call it parse expression, right? In expression we call it parse expression, and within parse expression, uh, within this expression is our this expression, this non-terminal is correspondent to this function parse expression, and within that we have primary expression. Primary expression corresponds to this parse primary function. Okay. And so parse expression functionality is like this corresponds to this non-terminal expression term. Okay. And parse primary corresponds to this primary expression. Okay. And in primary, if you look at primary expression is an integer, literal, or an identifier. Or we have within the brackets we have an expression. So that's what has been done with C. It could be an integer, literal, or an identifier. See if it's an integer, literal, or an identifier. Okay. And we create node from token. we have another function called token, create node from token. So based on the token type, we are creating the node. So if it's an int, so we are creating a node, literal int. This one we had, right? These types of nodes. So node type. So that one we are creating here. So type, if the token is int, so integer literal, then we are creating an integer literal node. If it's an identifier, we are creating an identifier node. So similarly, if it's a keyword and if it is exit, so we are creating a exit node. Why we are separating this exit node? Because exit node has in code generation we'll use this, right? Based on if it is exit call, we'll be making this move RX, right? It's final one we have to make this right, and in RDI we have to set in that parameter. So for that reason, I have to use this have to use this. So if keyword is exit, then I have to create a exit call node. And if it's an if statement, I have to differently create a if node and then integer. So node type specifier. So here node type specifier I have only done for integer. So character, if I had done integer and character, I would have specified a node int specifier and node char specifier. And if it's none of the above, I'm going to assign it as unknown node. Okay. And finally, value str. So I have this right. So if it's a keyword, I have to store that keyword also. Just like the identifier, I'm storing the identifier, right? If it is int ABCD, it's like int ABCD. I'm storing this ABCD, right? See over here, I'm storing it, right? In this union, the str well, I'm storing that ABCD, right? Same way, exact same thing I'm doing on here. For exit if an int, I'm storing that exit if an int into that this string line. But in case of integer literal, I'm just storing as a null right now. But that value I already made earlier, right? If you look at price expression, primary, parse primary. So if we see here token type equal to int, we are calling this create node from token, right? So here, mm, after the switch case, here we are setting it to null. But after, if you look at over here, we are creating the node, right? We are creating the node and sending in the value str. That value str for all other tokens, that value str will go in, okay, and node type, uh, based on node type, the int value will be set. Okay. Create from token uh, type. So here we have type, right? Type is node. Yeah. If it is a node literal int, then the int value will have whatever value we pass in as this value str. But here value str we're passing in null, so it will have the value null. Okay. But if you look at this line, if type equal to I am compensating over here. So if type is node literal, then I'm setting the node's integer value to token dot value dot int val. So if we look at token, token also has a value, right? And within that value we have int val. So that is placed into here. Yeah, it's been placed. Okay. So I didn't pass in there because I didn't have token, right? Did I have token? I couldn't pass in the entire token over here. I could only pass in token dot line and token dot column. So that's why if I have access to token, then only I could dereference value and also integer value, right? So that's why after this statement, I set it into node value and in node values int val as token dot value dot int val. See, in this case, I am only sending the line and column number, right? I'm not sending the entire token. So that's why here, uh, after creation of the node only, I have to take in node value dot int val, and after that I sent in the tokens integer value into this integer literal token. Uh, uh, no, sorry, this is integer literal tokens value into integer literal node. Okay. So I couldn't pass in here. Right? See, if you look at, I have type, I have value, I have line number and column number. So I couldn't pass in over here. So right after this line, I have to take in token, and through token, I could get the unique. So that's why I handled this case earlier. Yeah. So back to this. So we were over here, right? So primary expression will also have expression. So let's look at primary expression. Primary on this one. So this is our primary expression. So primary expression could be integer, literal, or identifier. Integer, literal, or identifier. Okay. And now I'm looking at if it is a separator token. Separator. This is a separator, right? You can go through my lecture video, you will get to know that this is a separator. Mm. So if we have this bracket, that means possibly we are going to have an expression. So I am going to send parse expression. So exactly this one. After primary expression, I'm going to call this expression. So that expression will I call after this opening bracket. And after that, I should also have a closing bracket, right? After this parse expression, I also need to have a closing bracket. So if it is not the case, I'm going to tell it's another. Okay, I expected this bracket. Okay, and I'm going to return this expression, this node. So this node, then I uh, return to my expression, parse expression. This will become my left portion. And if you look at this left portion, if you look at this carefully, see this left portion is the primary expression, right? So that's why here, see, left portion is the primary expression, and then we have the operator, right? So I pass in the operator using this value, um, and after that, then the right portion is my parse expression again. So if you look at over here, primary expression, right? Primary expression, operator, and expression. So this is the left portion, this is the operator, and then this is the right portion. So that's exactly what I did over here. If you can see left portion is the parse expression, parse primary functionality, and then I have my operator, then I have my right portion, which is the parse expression again. Okay. and I put it in a while loop because I might have any number of expression. So to pass any number of expression, that's why I put it here in while loop. And then uh, the reason why I put left and right is that then see, remember I told you I have a tree, right? This left child, right sibling. So I'm reusing that tree for my expression as well. So for my expressions, I'm using the normal binary tree. Why? Why? Because I have to see. If you look at this expression, a plus. See, this expression is a plus b into c. So b into c should be calculated first, right? As per the precedence. Multiplication is having more precedence than addition, right? So b into c gets calculated first. Then we have a plus b into c. So b into c is say d is the result. So we have a plus d. Then a plus d is say e is the result. So a plus d is going to give e. What I'm saying is we have a plus d into c, right? So let's say b into c is d. In that case, this becomes a plus d. And let's say a plus b equal to e. So in that case, this will become E. So firstly, this has more precedence, right? Multiplication. So A plus C becomes D. Then last, we have A plus D. So A plus D becomes E. So I'm reusing this tree for my expression tree. But while I'm using it in my expression tree, I am using it as a normal binary tree. So for that reason, my left portion is going to be parse primary and my right portion is going to be the rest of my expression. So in this case, a plus b into c. So in this case, my primary expression is a. Okay. And my operator is what? Plus. Right. My right portion is rest of B plus C. So left equals operator operator is this one and right is my rest B into C. So that's what I'm doing. Uh, rest goes to right portion and my operator. I'm reading my operator and this left already I have accumulated and see also see this here a could be an integer literal or an identifier and that identifier if you look at this identifier uh, I'm taking it see I'm finding it in the scope stack. Okay, so from the tables this table that I took, so this way I'm traversing and finding that particular symbol. And then if you look at here noise expression also binary, then I have this symbol, then I'm converting it into integer literal. So even if it is an identifier, then also I'm converting it to integer literal. So if you look at here, so for integer literal, if you look at in create node from token, you can see that case int. Okay, case int. See the token goes in, right? And token has a type. So token type, if it's an int, that time also we are converting the type into node little int. So integer little. And also if you look at Also, if you look at for identifier, after reading it from the simple table, I'm converting it into I'm creating the node directly instead of doing from create node from token. This will internally call create node, but here for identifier as well, I'm creating it as a node, as an integer little node. Why? Because see, if you look at a plus b into c. So here if you look at say A is 10, B is say 20, C is say 30, and I'm not adding here this stuff or this stuff. So this would change the value of A, right? So if I had instead of this, if I had, like this, or if I had something say like this and then A. In this case, A would be updated to 11. And then here, when we read A would become 11, right? So uh, in my language, I don't have prefix and suffix operators. So that's why I can directly just read the value of that identifier from the single table and placing the values. So that's why I'm converting it directly into integer literal. So that's why I'm creating as an integer literal and just passing in the value. So I'm creating the token, creating the node and passing it as a and placing it as a constant node. So now finally what I'm doing here is parse primary was parse expression, parse expression. So this is my left portion and this is my right portion. I have my property. So I'm placing this as a binary expression. I'm making a binary expression tree. So my left portion will have this left portion. That binary expression tree will have my left portion and the right portion, the rest. See, the left portion will have this A in this example, and A into C will be placed in the right portion. Okay, and the operator here would be C left is A. Okay, operator is plus and right is A into C, and so the tree will look like this: operator equals operator plus, right, and this one's operator left equals operators left equals A, and operators right equals A into C. So this is my tree right now, binary expression tree. So that's what I'm creating here. And why am I doing this? Now here I bring in the concept of constant folding, which is again, no, it's a compiler optimization technique. So what is it actually? What we are trying to achieve? Say we have 10 into, say let's do this 10 plus, let's take few examples. 10 plus 10 into say 2. Okay. So how do we evaluate this? Firstly, we are going to evaluate, we have precedence right here. So addition has less precedence than our multiplication. So this will evaluate into 10 plus this should be evaluated first, right? So that's why 20. So it will become 30. So finally, this entire tree would be compressed to just one value, is 30. And this done through this evaluate constant expression. So this is the function which will pass through the tree and give us the node, final single node. Instead of this, see, this is going to be a tree. Okay, 10 plus is going to be our operators plus, and operators left equal to 10, and operators right is going to be 10 into 20. So then this one's further, this operators rights operator is going to be what? It's going to be the star, right? Multiplication. So this one's left is going to be what? This one's left is going to be 10. And this one's right is going to be what? This multiplication operator's right is going to be 2, right? See this is the operator, its left is 10 and its right is 20. So finally I'm going to do in order traversal and get final value as 30. So that how I have I done. If you look at over here, we'll be passing in, see, I passed in that tree, right? That entire tree. This entire binary expression tree I have passed in. And here in the evaluate constant expression, firstly, I'm going to see if node type is no, this the base condition. The base condition is going to be until I reach integer literal node, I'm going to pass through the tree. And if I reach the integer literal, I'm just passing in the value. So its return type is int. So I'm returning that node's value. If it's an integer literal node, I'm just passing in this. If it's until I reach this 10 or this 2, I'm going to pass through the tree. So for example, here, say if ABC, you see in my case, I have converted identifier also as integer literal, right? Because I'm reading from the symbol table and I'm creating it as a integer literal, right? So that's why I have made it simple, because I don't have post increment and pre decrement, or post uh, you know decrement and pre decrement. So that's why I can just keep it uh, as a common integer literal. Okay. After reading the from the symbol table, I can just keep it in as a integer literal. Okay. So I'm the base case is I'm reading this and passing the value, and I'm just double checking that it's not a node identifier, in which case I have to just exit. But as I already told, that node identifier, I'm creating it into node literal, integer literal on node, right? So that's why, anyway, if I just get that entire expression tree, it will only be uh, integer literal. So we are only dealing with integer literal in my entire binary expression tree. So if you look at here, we are going through, what are we doing here? We are doing here this one, right? We are going through the leftmost part, and here we are going through the rightmost part. So for example, if I have a bigger expression, let's take a bigger expression. And yes, so is my tree going to be? My tree would be something like this. So this portion, okay. Then this portion here. Then further this will also break down. So this will become my operator. This will become my operator. When that is my operator, so this will become my left part for this operator and this one. Okay. And further this also breaks down. So here the operator is multiplication, right? And the left part is going to be 10 and the right part is going to be 2. So this is my tree finally for this expression. Okay. And how am I building this? I'm building it as per precedence. So precedence of multiplication is the highest, right, in this expression. Multiplication has higher precedence than addition, right? So the higher the precedence, it will be at the leading. Okay. So this is the exact thing I'm building here. If you look at before I come on here, let me just go to calling. Sorry. So where did I call get precedence? Yes, get precedence. So this get precedence, I have the precedence here. Okay. I set for multiplication and division the highest precedence. Also for modulus operator has highest precedence. After that I have addition. After that I have this left shift, right shift. Then greater than, less than, equal to, greater than, equal to, then double equal, not equal, then bitwise operators. So, so as you can see, the highest precedence is for multiplication and division. So in our normal C program also, this having the highest precedence, right? So the exact same thing I have kept here. So what I'm doing here is, how am I creating this? How am I creating this tree? How am I creating this tree? Firstly, I have a main precedence that I'm passing. If you look at whenever I'm calling this from another function, my min precedence I'm sending it as 0. So you can see here I'm calling it from variable declaration. So in variable declaration also I'll have expression right. Say for example x equal to 10 and x equal to this expression. Okay. So I can have this, right? In C program also I can have this, right? So that's why in variable declaration I'm calling parse expression. So whenever I'm calling parse expression, as you can see here, I'm sending in the value 0. So minimum precedence is going to be 0 initially. And right now precedence of plus is what? Right now we are at plus. This is our operator right now. So, and 10 is our left portion. Just let us keep track of this. Left equal to 10. How left is 10? From parse primary, I'm going to get my integer, uh, integer literal, so which is 10. In case if it was some a and a was equal to 10, in that case also left is going to be 10. Okay. So left is 10. Now my operator, here I have operator. Here I'm reading the operator. Operator token equal to next token. Next token is what? Next token is this plus. So operator would be equal to this. Okay. Then I have parse expression. Then I have parse expression. Parse expression is going to be this. So let me keep this in back 10. Right is equal to this. And this is parse expression. So again, internally, this will call for this one, this expression. And here again, left is going to be 10. And here operator is going to be plus. And here the rest left out part is 10 plus 10 into 2. And again, this would be called, because this is parse expression, right? Again, this would be called, for this, we have left equal 10, operator is multiplication. The right portion is 2. So finally, we don't have any more expression. So we stopped at parse primary itself. So here this condition fails. So finally we created this tree. How we are creating this tree? See, initially we had left as 10, right? So left is 10. We got this. And operator was what? This addition operator. So we got this addition and left is this. Then rest is what? After we have 10 and this one, we have 10 into 2. Okay, so let me create this tree again, or let me just copy this. So I created for this expression only. So I created for this expression. I will copy this entirely and place it where I make for this or this one. No, I made it for this. Uh, this one. No, I made it for the entire expression. This one is. So let me just place it here. So let's see, try 10 and 2. 10 plus 10 plus 10 into 2. Yes, right. So initially, operator is this part, operator. Okay, left portion is our 10. Left portion is of 10 and right portion is rest. Okay. So left of the tree, the uh, first initial thing is plus, then left portion is this node, then right portion is this entire subtree. Okay. So this is the entire subtree. And then we again break it down into this 10 over here. Then we have this plus, so this piece, and then this portion here, 10 into 2, which is the right portion, is again broken down into 10, then this multiplication, and this 2. Okay. So this is how the tree is created. This is how the entire tree is created. So after the entire tree is created, we send it to, no, uh, we send it to here. The operator token I'm creating, see this operator is there, right? This plus. So this plus, I'm creating that as the root node, and then it's left and right portion. And once that is being created, that entire tree is passed to evaluate constant expression. And at evaluate constant expression is where the constant folding happens. So constant folding is, as I told you, this 10 plus 10 into 2 will be evaluated to 30. So directly that 30 value is placed into our particular variable or our computation where we are trying to place. Okay. So evaluate constant expression. Here we go until we reach the our base condition. Our base condition is until we reach integer literal. So when we reach an integer literal, we are just passing that integer literal's value as an integer. Okay. So node value dot int value has that value of the integer literal. Then so left portion will keep traversing left portion. So for example, in this tree, the left portion is 10, right? And here we are going to the right portion. So until we reach the end. So here we reach the end. So in this case, we got 10. Okay. But in this case, we got this entire tree. So initial left, if you look at, so initial left equal to 10, and then the right equal to this portion, 10 plus the expression of this, right? So the right portion is this one, this entire thing. Then this right portion is not, see, the left portion when we read, then we are returning it, right? See, when we reach an integer literal node, we are returning. In case of right, it's not integer literal, so we have to uh, traverse again. So how do we traverse? Again, left and right, we have to left and right side of the tree we have to traverse for this subtree. So right's left equal to 10. So this reached uh, its base condition. But again, right is still pending. Right is equal to 10 quotient, right? 10 into 2. So this will be further split, right? Because we haven't reached the base condition yet. So that's why now this will further split into rights, left is equal to 10. And rights, rights, right is equal to 2. And again, what is the operator here? Operator is plus. Here, operator is what? Here also operator is plus, right? For this expression. Then for this expression, what is the operator? Operator is into multiplication, right? So finally, the entire tree we reached at the base case. This one and further anyway it won't go down, right? So we reached at the leaf nodes. So at this 10 and 2. So when we reach the leaf nodes, if you look at see when we got left will have its value, right will have its value. So in this case, 10 and 2 would be the value. Okay, 10 and 2. And the operator is the node value dot str val. So this is nodes left and nodes right. So see this portion of the subtree, this the nodes value, right? This the nodes value, which is this string, right? This into, and its left portion and right portion is 10 and 2, which we received, right? So right after that, we have the operator and this 10 and 2, right? So what we know now? Now, if operator is plus, we just do simply left plus right. If it is minus, left minus right. If it is no multiplication, left into right. And for division, we check if the right operator. See, we are doing this right. For division, we'll be doing left divided by right. So right should not be 0, right? Only then we can perform a division in integers, right? That's what we are checking here. If it's a division, if right is equal to 0, then we are going to exit because its division by 0 is not possible. So we print that and exit. Otherwise, we just return left digital. So similarly, for all other cases, this bitwise operator and bitwise XOR, then left shift, right shift, this left shift, then this is the right shift, then double equal, and similarly all operators. So everything is handled over here. And finally, we just return, right? So in our case, we had 10. In our case, we'll go to this portion of code, which is this portion. So left into right. So left into right. So 10 into 2, which is how much? 20. This would evaluate to 20. And this 20 would go over here. This 10 into 2 will be 20. Okay. And what do you have here? Finally, we have 20 is placed over here. Then here we have 10 plus 20, right? This one 10 plus 20, right? So how much 10 plus 20 will be here, right? Sorry, not this one. So 10 plus 20, right? So left plus right. So what do we have here? 10 plus 20. This is 30. Okay. 30. So that 30 would be evaluated by this. So that 30 goes inside here. Then finally 10 plus left plus right, right. So 10 plus 30, which would evaluate to 40. So finally we have 40 only. And this is our final result, which will be returned. So 40 would be returned finally. Okay. So this is how the entire expression tree would be working. So it will be working on precedence, and it has this compiler optimization technique of constant folding. So that is what I have applied here. So similarly, if you look at this grammar, I've also done for uh, variable assignment. See if you look at parse, parse, right, parse. I'm doing parse statement. Okay, in parse statement, if it is variable declaration, I go into that. If it is a keyword and it's starting with if, or it is starting with else, I'm then going to else, parse else. This one. There was parse else. Also statement, else statement. This is the parse else. Okay, this is the parse else. Parse else. And then if I have while, I'll go into parse while, right? So was while. So while this one while statement here while statement I have. So that while statement is passed by my here parse while statement. Similarly do while then parse block, right? And parse assignment. So if I have this identifier, then I have followed by these assignment operators. So I'll go into parse assignment statement. So this is the overview of entire this grammar, how I'm handling in functionality. So this grammar provides me the overview of how it gives me a blueprint of how to uh, how I have to build in my functionalities. So if you look at see block statement, if you look at block statement, if it is calling interim statements, so you can see in my case, if you look at for example here block statement, parse block, right? In parse block, I look at this opening bracket. See this opening bracket. Then have to parse again the statements. Then again I'll pass in the statements, and then I'll looking for a closing bracket. See, looking for a closing bracket. So there are I'll split this question, as in I covered the expression part. So in next I'll cover the block statement and if block. Okay, so using that concept, I can move into while statement block and do while statement block. And with that, this entire syntax and semantic we can complete. Okay, so I split this into three parts. So one is this part. Another part would be, as I mentioned, the block statement and the if block statement. The next third last third part would be of while and do while.